Hello all. In this video, I'm going to introduce you to the basic ideas of genetic algorithms. We're not going to get into any of the fancy, complicated things that people have done that are wonderful, and you should look them up. We're just going to take a look at the basic functioning of a genetic algorithm and how it relates to the other local search methods that we've been looking at so far. All right, so there's a whole family of related techniques here. They go by different names. So genetic algorithms is one, genetic programming is another, evolutionary programming, evolutionary algorithms. There's a whole family of approaches. They have distinctions. Genetic programming, often the representation of the problem or the state is actually code in some form or other. And with genetic algorithms, we typically have more string-like or array-like representations. Fundamentally, the distinctions are not that important for us at this point in time. So it all kind of falls under this heading of evolutionary computing. Okay, what is the key idea? What are the key ideas for us for genetic algorithms? We want to simulate a simple form of natural selection. Natural selection and evolution are extremely complex mechanisms. People have been studying them for a long time. We're taking a very, very simple view of natural selection and we're simulating it as a problem-solving method. So what we want to do is to represent our potential solutions, our states, as strings of some kind. And oftentimes we think of this as, if you look at the literature, you'll see it talking about these as like chromosomes and using all of the terminology from natural selection. And that is a perfectly valid way to think about these. Oftentimes the strings are a condensed, compressed representation of the solution that we can then unpack and turn into an actual agent separately. But fundamentally, we want a string or an array of numbers, a vector, that represents our potential solution. Then we're going to create an initial population by generating random strings to start that population. Notice how, if you've seen the beam search video that I did, notice how this is akin to what we're doing in beam search. It's just that we're being a little more specific about how a state is represented in this case. The next step is to evaluate the fitness of each string. This is that objective function, evaluation function, fitness function. It's all the same idea. Each string has a value that represents its quality as a solution, and we want the same things out of a fitness function that we wanted out when we were talking about local search. Something that has a spread of values across different states. So you have lots of gradations of quality that a particular solution could have. Where genetic algorithms gets really different from the other local search algorithms is in what happens next. These two lines. Because always before, we thought of the state space as having neighbors that were similar in form. And I guess mutation is the closer of the two to what we've done with hill climbing and other searches. Here, we're not really thinking of neighbors in the same way, and we're adding in mechanisms that can take you with one step quite far away in the search space as we would normally conceive of it. So what we do is we do a little bit of what's called resampling. So this step right here is resampling, and it is often implemented as roulette wheel selection. We select parents from the population where the likelihood of being selected increases as the parent, as the state or the string has a higher value. So we select high-performing parents from the population, and from those parents, we generate children. We do mutation on those children, so that mutation is kind of like what we do with thinking of a neighbor in hill climbing terms. So we make a small local change to this string that represents our solution, and we get a new solution that is a neighbor. So mutation works very much like what we were doing with hill climbing, but we also add in another mechanism, which is typically called crossover. And crossover does not really have an analog in the other local search algorithms. Crossover is where we take apart the strings that are the parents and we recombine them together. So you have a new child that has a mixture of the values from both of its parents. And we'll talk a little bit more about this later on. But this is a new mechanism. It's not something that we've seen with beam search or any of the other hill climbing algorithms. All right, so that gives us new children for the new generation, the same number of children as there were parents in the previous generation. So when we pair up the parents, you have a pair of two parents, we do this crossover with those two, and we get two children out of it. So we always keep the population size steady for us. And then again, we just keep repeating this process over and over and over until we get the solution quality that we want. All right, so this is just rewritten into pseudocode. Start with a population of random strings. You repeat until you're done. You calculate the fitness values for the strings in the population. You select parents from the population weighted by their fitness. You cross over parent strings to produce k child strings, and then your new population is the result of applying then on top of crossover, applying mutation to the children. This is a really common formulation of this genetic algorithm process. There are a couple of things that I want to talk about. I have it kind of broken down by each step of the algorithm. So I'm going to talk through those and we'll kind of look at the notes. We'll keep coming back to this algorithm as we go. So for the first step of the algorithm, the very first thing you face is you need to generate k random solutions. We haven't, when we've been talking about the other algorithms, we didn't really worry about what the representation was for a solution. Here, in order for us to do crossover and mutations most easily, we need something that's a one-dimensional collection of data. It could be a string, it could be a vector or one-dimensional array or a list. We need something like that. So one of the things you have to think carefully about when you're trying to implement a genetic algorithm for a specific problem is how are you going to represent solutions in this format? We looked in an earlier video at the traveling sales problem, and in that case what we had as our representation of the state of a solution was in fact a string. It was the sequence of nodes from the graph. You could think of that as a string. You could make that be your representation. But each problem, you have to think again about what the best way would be to represent that problem as a vector or string. And you can have more complex representations. As I said before, there are even some like versions of this where the representation is actually code of some sort. You're coding up a solution. That just makes all of the other steps, particularly crossover and mutation, more complicated to implement as well. So it's doable. You just can't use the most simple forms of crossover and mutation. It's also the case that you don't have to just generate fully randomly the states for this search. So if you, for instance, have some inkling of what a good solution might look like, rather than generating all possible solutions with equal likelihood, you could instead generate solutions that have particular properties that you think are likely to be good properties. You're kind of like, putting your finger on the scale. You're twisting the algorithm so that it looks at a particular part of the search space. That could be bad if you're wrong, but oftentimes it's a way to speed up the search and get us in the realm of a good solution faster. Step 2 is the step in the algorithm that says repeat until done. You could decide on a number of different criteria for when you're going to stop the search. If you know what an optimal solution is, you can keep searching till you find it. You could also decide that if you exceed some threshold of quality, you'll just stop regardless, even if it's not optimal, but it's above some reasonable threshold. It's also the likelihood that you could look at the population's quality overall. So maybe you just calculate the average quality across the population, and when the population as a whole reaches a certain point, you stop. It's more common that we look at the best individuals and we stop when they exceed some threshold. All right, the next step in the algorithm was 2A. This was calculating the fitness values. We haven't really talked about how objective functions work, but there are, within genetic algorithms specifically, there are different techniques that are common alternatives that you could use. So there are many ways you can evaluate the fitness. You could have a function that takes in the encoding and it uses some kind of mathematical formula to produce a fitness value. If you can do that, that's great. Maybe we're trying to maximize a function of some sort, and so this is exactly the way we'd want to do it. You may be faced with a situation where there is no known function, so then what do you do instead? If you can't come up with a fixed function, you could instead run some kind of a simulation on the encoding. In our case, we are talking about AI problems. We typically have this idea of an agent in an environment. So you could run simulations of your environment with an agent in it who is embodying one of these solutions and evaluate how well it turns out for them. How well did they succeed in that simulation? So that works very well for certain kinds of problems. You could also run a tournament of sorts where you have different solutions, different encodings or different solutions, all competing in the same space together. So a classic example of this is if you wanted to use a genetic algorithm to evolve a really good tic-tac-toe player, then you could have tournaments where the different possible solutions play against each other, and you keep track of wins and losses and the points that are won in a particular game, and then you use that to compute their fitness. There are lots of other ways you can do this as well. The next step is talking about selection of parents. So statisticians will call this resampling with replacement. Computer scientists often call this roulette wheel selection because that's the way you think about the algorithm as opposed to the concept. So we'll start by exploring the statistical perspective on this problem solving. So we have calculated fitness values for all of the individual solutions in our population. So here I've redrawn our diagram from before, but with more points because typically we want a larger population size when we do genetic algorithms. They're scattered around the space randomly. We've calculated their fitness, which is their height, their vertical height. And we think of that as sampling from the probability distribution that is our objective function. So we treat the objective function as a probability distribution, and we're sampling values at different points. So using those probabilities, the probabilities of the points that we've actually calculated, that lets us estimate the probability distribution, lets us estimate the objective function, right? So what we'll do is treat the values as the likelihood with which each encoding will be selected, and we will resample, we will reselect from these points. The with replacement part means that we allow the same point to be selected multiple times. This is actually exactly what we want. If I have a point that's up here and it's of very high quality compared to most of the other points, I would like it to be selected multiple times because it's a very promising place to explore. So we'd like it to be apparent many times. And so maybe we can generate other points that are in the same region as it. This kind of goes back to the fact that this is a model of natural selection. We're thinking of survival of the fittest, where the fittest individuals are going to generate the most children because they're the best. And we want them to breed the most. All right, so how do we go about actually doing this resampling? That's what the roulette wheel selection algorithm is all about. So what we do is to imagine that we've got a roulette wheel that has one wedge of the wheel assigned to each individual in our population. And one of the rules we do with genetic algorithms is even the worst individual gets a slice of the roulette wheel. You can violate that rule. It's just a general rule of thumb, but it's often the case that we do that. So if all of our individuals were equally good quality, they were all somehow at the same level, we'd get a roulette wheel that looks like the picture over here on the left. Each one gets an equal wedge of the pie. But they don't. They have different fitness values. So what that means is we give a section of the pie that's proportional to their fitness value to each individual. So A is kind of not really highly fit, B is better, C is really pretty good, D is not so good, F is terrible, but it still gets a sliver of the pie, G is also pretty good. Right? So you can see that they have a different size of the pie, of the roulette wheel, depending on their fitness values. And then we just spin the roulette wheel enough times to generate parents. So more often, the high performing individuals, the high fitness individuals will be selected. It's going to be a pretty unlikely occurrence that F would be selected, but there's a chance that it could happen. And we want that because we want to maintain genetic diversity, solution diversity in our population. We don't want to throw all of our efforts right away at one particular part of the space. We want to search the whole space fairly well. And this is one way of doing that. We just keep some churn in the population of having low fitness individuals continue to exist and continue to mate. So then, yeah, if I have, what do we have? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 individuals in my population. It's very small. Just as an example, you'd want many more if you were actually implementing this. I can just spin this wheel 8 times, and whatever individuals come up, those are the ones that are selected to be parents. And from them, we will generate then the next population. All right. I'm going to go back to the algorithm for a moment. We've looked at this step, and we've looked at selecting the parents. The next step is to perform crossover, and this is where I want to show you a way that you can do crossover, the simplest methods that people use that are predicated on the fact that you've got a string or an array as your data, and then we'll go from there. All right, so the most common way that you do crossover is, first of all, you have some probability that you don't do crossover, that the parents just continue on into the next generation intact as themselves, or maybe with some mutation applied, but without doing any crossover. That just allows us to preserve good individuals as is with some likelihood. But most of the time what we want to do is to cross them over. So if crossover is performed, we compute a random index into the strings, and then we slice the string at that position. So I have an example right here. We have 2 strings of numbers. This is our encoding of our solutions, and we say the random index is 6, 0, 1, 2, 3, 4, 5, 6. We're going to have 6 be the last value that's in the first part, and then the position 7 and onward is going to be what remains. So you can see I then split them at that randomly selected cut point. What do? Well, then we flip them. So we can take these last sections and just swap which one belongs to which individual. And so now child 1 has the beginning of parent 1's string and the end of parent 2's string. And child 2 is the opposite. It has the beginning of parent 2's and the end of parent 1's. So this is an easy method. It's just a little bit of string or array manipulation, and we can generate new strings. Now, why would this work? Isn't this really disruptive? Well, it can be, But oftentimes what you find is that there are subsections of this encoding that kind of go together. And so maybe it's a combination of the 5 and the 1 and the 9 that cause this to be a high performing individual. And when they are relatively close together in the string, they are preserved from one child to another most of the time. And that allows us then to generate variations where we're changing the behavior of part of it, but we're keeping sections intact. And it could be, imagine that you would have a scenario where this early part of the string is responsible for parent one's value, and maybe the last two numbers in parent 2 are responsible for its high fitness value. So we take those and we put them together, and now child 1 here is a powerhouse. They've got good things going on from both parents, and they have a higher fitness than either parent alone. That's our goal. All right, the last step in the algorithm is mutation. Again, this is dependent on exactly what your representation is, but fundamentally you have some small probability at each position in your string, in your representation of the solution, that it will be mutated. And so if it is mutated, then you change it to another acceptable value. And again, that exactly what that means depends, is very problem specific. In this case, I just have individuals, then they're changing from one number to another, and that's easy enough to do. If you had something like the traveling sales problem, you would have to look at, say, 2 adjacent and then randomly decide that you're going to swap them. And again, there are a million different ways to decide how to handle that mutation depending on the problem itself. All right, I'm going to stop there. You really do need to play around with genetic algorithms to truly get a sense of how they work. And there are so many additional variations that people have invented over the years. It's a very large area of research, and it's got a lot of really cool applications. I can't list them all because they're just too many. So I encourage you to do more exploration. This is just a hint of what happens when you implement genetic algorithms. One thing I'll note is that this is relatively simple code. It's relatively easy to start from scratch and write a genetic algorithm for a specific problem. And so I encourage you to experiment with that as well. I will see you all very soon.